Hello and welcome back to Calculus 3. This is section 15.2 on limits and continuity. Limits are going to get much trickier than what you had in Calculus 1. In Calculus 1, you have a R2 function, right? X is input, Y is output. And if you never before understood limits, it's very simple to think of limits as a fancy way to calculate the Y value of a function. That's all it is. Because the answer of every limit is just the Y value that you can, in some cases, compute by simply plugging in the number, and in other cases you would have to use either clever algebra tricks or maybe chart or a graph or something like that. So going back to Calc 1, let's start there. So Calc 1, we have limit x goes to a of f of x to give you some value L. And the picture, the graph that we can draw along with it would be something like this. You are considering the value a, and it's supposed to produce the answer L. So that's the basic. Now the way this happens is in the problem over here we say we approach A. Now you can approach A from the left, which is you walking up this line, which is actually going up this line towards L. And then you go from the other side, which is going down the line, which is going down this L, down this Y, again towards L. And because they meet at L, you have a limit. Now, if there is no limit situation, you have something like, let's say, 1 over x as you approach to 0. As you approach from left, which is red, you would go down the y-axis, and when you approach from the right, you would go up the y-axis. And they do not meet. And that's why there is no limit, because the left approach and the right approach gave us different numbers. So what is a limit? Limit is a fancy way to compute y value. As simple as that. Now, sometimes that method is the same as just calculating value of a function. So you have, let's say, limit of x goes to 3 for x squared, and you just plug in 3 squared is 9 and you are done. So that's the cheapest you can have. But in some problems, you might have limit x goes to 3, and then you have x squared minus 9 divided by x plus 3. X minus 3, let's say. X minus 3. So now in this case, if you plug in 3, you get 0 in denominator. And that's an issue. But luckily, you know that you can factor out, right? You can factor the binomial, and then this x minus 3 would cancel, and now you have a problem where you have limit x goes to 3 for x plus 3, and that's just 6, right? So some problems you can straightforward plug in and be done. Other problems you have to massage with algebra a little bit. And a third type of a problem is where you would actually have to look at a graph and see what is happening off of the graph, or do the chart of values. But the idea for the limit is simply we are calculating y value. Now, why did I say fancy? I said fancy because we are actually computing at every value prior reaching to A, and we never calculate at A. Now, I understand that this is calculating at A, but it just works that way because there is the answers for limits and answers for pre-calc when you plug in value need to match, right, in terms of calculating function, calculating the limit. Now, there are cases where limit and the function value are not the same, but those are the extraneous cases where you have a function with the open circle and then that point is displaced. Now, in nature, right, we don't see this too often. Obviously, if the section of the bridge is missing, you're not going to drive over that bridge. Should be common sense, right? I mean, if you drive over the bridge and you fall off and you just boosted the IQ, average IQ of the country. So the idea over here that at this A, right, the limit would be here and f of a would be here. So for some situations like that, right, that are extraneous situations, there's nothing extraneous about x squared. It's just a parabola, or x cubed, or square root of x, or ln x. There's nothing extraneous about those functions that are, right? But there is something about this function here, because there's an open circle and the point is dislocated, right? You have to do extra work to make that happen in reality, right? So when you look at the limit and the function value, they're not the same. But when everything goes smooth in life, they are the same. Now, why did I have this big story about Calculus 1? Well, now Calculus 3 is going to have a huge issue of the domain. When you consider Calculus 1, you see the two arrows, the red one and the blue one. I call them Romeo and Juliet, okay? Because they approach the same location at the same time, and then they meet and they're all happy, right? We all know that this is what happened at the end, right? If you read the story, you know. Just to spoil it for everyone, they die because they're dumb teenagers. But the idea is when you look at the limit, right? When you look at the limit for R2, the only ways to approach A is to approach from the left, which is red, or approach from the right, which is blue. And we have those defined as limit x goes to a minus and limit goes to a plus, right? Those are the notation that we use for the left and right approach. But that's it. That's all you can have. Now consider R3 limits. So we are back in Calc 3. Your domain is two-dimensional, and you have some surface on top. In how many ways can you approach a point on a 2D? You see that? That's an issue now. So R2, the domain was just x-axis. So you can approach from the left, or you can approach from the right, your point A. Now look at R3. R3 domain, so this is R2 domain, is just a straight line, x, the only input you have, and you can only approach from left and right, and we have left and right limits, and that's it. But the R3 domain, guys, R3 domain is insane. I have a point here, AB, which is the input. For all purposes, I can spiral in. I can approach this way. In how many ways on the surface of this floor can you approach my desk? Sure, you can approach my desk in a straight line, right? Which most of you will, because it's a flat surface and the shortest distance is a straight line, right? So here's the desk, and then the straight line from your seat. Nice. That's a straight line approach. But then the other student is going to approach from to the same point, from a different direction. Let's say there was a student over here who had a party last night. Also approaches my desk. Different function, but still here, still asking questions, right? So we see the issue now. this story of the two-way approach goes away, because now we can approach a point in 2D in infinitely many ways. It's not just infinite directions, it's also infinite functions on top of everything, which creates a living nightmare to compute limits. And we still have the three different levels. There is a level of limits you can just plug in, the limits where you use some algebra, and limits that you show that don't exist if you are able to show that two different paths give you different value, which is equivalent to, remember, two students approaching, right? If you approach from this path, right, one student approaches my desk, and then another student approaches my desk. Well, if they both approach the point, which is my desk, but there is a different outcome at the desk, so one approaches and it's me, the other student approaches and it's not me, it's someone else. Right? That makes no sense. In that case, there's no limit. So, three levels. So let's go with easy. Easy is when everything goes smooth. When you plug in the number, you get the value. So the limit, let's say, x comma y approaches 1, 3 for x squared y minus x plus 6. No zeros in the denominator, no vertical asymptotes, no interruptions in the domain, nothing weird is happening. It's not piecewise function, so it's just a polynomial looking formula, and you plug in 1, 3 and you get 6. So the easy one is just plug in, and if you get a value out of it, great. Another easy one, so let's say this is problem A. Problem B, limit x comma y goes to negative 3 pi over 4. The limit is sine of xy plus x squared, for instance. Well, you go, okay, sine function doesn't have anything weird going on. There's no asymptotes to make 0 in denominator, so no issues of any kind. I should be able to just plug these things in and compute and get a value. So that's why this problem is also easy. Yeah, it does have sine, but you should be able to compute it. So the answer is sine negative 3 times pi over 4 plus negative 3 squared. And so you just compute this thing. Sine is odd function, so minus will jump out, and we have 3 pi over 4, and then plus 9. For the sine, all students take calculus. Sine in a 3 pi over 4 is in a second quadrant, so sine will work out to be a positive root 2 over 2. So this is negative root 2 over 2 plus 9. Done. So when there are no zeros in the denominator, when you have a function that you can just plug in and compute and get the number, like we got 6, like we got this 9 minus root 2 over 2, you are done. It's simple as plug in and walk away. We start having issues when you plug in and you get 0 in denominator. In that case, you can have an answer, or it could be limit does not exist. So it can go either way. Now this is equivalent to this problem here, right? When you have 0 in denominator, because when I plug in 3, I have 0 in denominator. So plug-in method goes through the window, because 0 in denominator you cannot compute. Now 0 in denominator does not mean does not exist, because was it a 0 in denominator? Was it? Yes, right? 0 in denominator. 3 minus 3 is 0. 0 in denominator, what's the limit? 6, right? So be very careful to make those generalizations. because if we don't have it as a theorem, it means it doesn't hold all the time. Only the things that hold all the time in mathematics we have as a theorem. So once you plug in, right, once you plug in, you have to do a problem that will give you the, maybe to cancel or rationalize or do something. So the top part was labeled as easy because you just plug in. Now this next part, these are called boundary limits. And in parentheses, I will say denominator equal 0. And I'll put these exclamation points here written in blood. So what would be an example of something like this? Say you have limit of x squared minus y squared divided by x minus y, where xy goes to, let's say, 1, 1. So your first instinct for limits should be to plug in, because if it works out, you're done, right? You plug x and y in, and if you get whatever number, right, you are done. But when you plug 1, 1 here in the denominator, you get 0. And that means that we have to do work. So luckily for us, this problem is very easy in a sense that we can factor the numerator using the difference of squares and then just cancel and be done. So answer for this one is clearly 2. So we have limit of xy goes to 1, 1. And then the top is x minus y, x plus y, divided by x minus y. These guys cancel as a unit, and you are left with the limit xy going to 1, 1 for just x plus y. And now no zeros in denominator, none of that stuff. It becomes a very easy limit to solve, and we just have a 2 over there. So if you need to write a sentence in your notes, write a sentence in your notes. When denominator is 0, all bets are off. Meaning you can get a limit or you can get limit does not exist. It depends on what type of function you have. So if you have 0 in denominator, you cannot automatically claim does not exist, because clearly this problem would be wrong, right? Let's take a look at another example of this boundary stuff. So anything that will create 0 in denominator. So limit of, I have to be careful not to run into the last case, so I have to think very carefully, right? Because if I put whatever, I might run into a problem easily that it's actually the last case that we have to cover. It has 3 cases: easy, this one, boundary, and then the one at the end where the limit does not exist. What should we have here? How about maybe I should just take something from the book rather than making this stuff up. I want to have a square root of, let's say, 2x plus y here. And in that case, xy should go to -1, 2, which would create 0 in denominator, right? Because that would be -2 plus 2, and it would be a square root of 0. And then maybe have like 3x over here. There we go. So this is a problem, right? So this is a problem. Now you try to plug in. You see that the denominator has a 0, and that means that you can't do this problem that way. But then, luckily, you went to pre-calculus, and you know that you can rationalize, right, expression by multiplying the square root of 2x plus y and 2x plus y, like this. And then that gives you the limit of 3x square root of 2x plus y divided by 2x. Oh, this is not going to cancel now. Yeah, such is life. I should have just read the problem from the book rather than making it up on my own. Because you still can't do it because the denominator is still 0. So, still 0. All right, go to the book. Find the problem real quick, so, because we're not trying to sleep here, right? Me figuring out which problem is going to work for the method I want to show. So let's go to the homework real quick and pick up a problem. I think this one would work just by quick glance at it. It might not, I don't know, we'll see it. So the limit xy goes to 2. They give you y squared minus 4 divided by xy minus 2x. So when you plug in 2 and 2, that's the first thing you try, you immediately see that denominator is 4 minus 4, which is 0. So we're not happy, right? And at that point, you try looking for algebraic solutions, which are either factoring or, if you have square roots, rationalizing. Not too many choices there. So we are going to, in this case, again, factor into numerator is y minus 2, y plus 2. And the denominator is, you factor out x, and you get y minus 2. Oh, yay. That dies. And what you get is 4 divided by 2. The limit is 2. So you have, again, a limit where you guys had to plug in, got 0, and then had to factor, use algebra to solve this. And now the level 3. Maybe I should underline with orange. And now, non-existence of limits. Non-existence of limits is the third level. And for this one, we will look for two paths which provide different values of the limit to claim non-existence of the limit. It occurs frequently in the nature. It occurs many times in this classroom right now. If you want to understand this, right, because you want to build stuff and understand things, let's take a look at the corner of this desk right here. So this point here, and I can maybe place something at that. I have this paper clip. So this paper clip is at the edge at this point here, and this paper clip is at the elevation of 3 feet from the ground. Now, to the end that it's walking on this desk, approaching this paper clip, the limit is 3 feet, because this line going all the way to the bottom is at the elevation, the point is at elevation 3, right? But this same point is on the floor as well. And the ant that is walking on the floor, because there is this vertical drop, would approach with a different and get a different answer. So the ant walking here is going to have one value, and the ant on the floor is going to have a different value. These are known as step functions. Step, exactly, step. It's a little bit big to be a step, right? So you have stairs over there with a smaller step. So the approach matters. See, there are a whole bunch of approaches which are y equal whatever line, right? Y equals x or whatever, that the ant on the desk is going to approach and get the value that the limit at this point is 3 on a z elevation, because the limits in 3D are computing the values of z with the xy input. The ant on the floor, however, the ant on the floor is going to take a different function and approach the same xy location. Remember, we can use the grid to come up with what's x and y for this. 1, 2, 3, 4, 5, 6, 7, right? So you know what the xy point is. The ant on the floor will take a different function and arrive at a different path and arrive at a different value for z, because the value would be 0. Because this clip, right, is on the xy dot, which, if you approach from the desk, is 3 feet tall, but if you approach on the floor, it's on the floor, the same xy point. So having a different limit means that the limit doesn't exist at that point. So technically, any vertical drop, you can see the limit doesn't exist along the line in this case. For every one of your desks, the limits don't exist at the edges here, right? Because there is a vertical drop going down. So if you approach from one way and you approach from the other way, you don't have the same z elevation. That's what it means for the limit not to exist when you have a vertical drop. Now in Calculus 1, you had that as a step function, something like this. That's a vertical drop between the 2 points. So you go this way, the value is 3. You go this way, the value is 1. 3 is not the same as 1, so there is no limit there. So now, when you have this situation for the non-existence of limits, you are going to take a look at, again, this is the domain. So when you are looking at the domain and you have a point that you are considering, if you are able to approach that point one way and say that, I don't know, z is 6, and you are approaching it the other way, and you find that z is equal to -4, then the limit doesn't exist, because two different approaches for the same point, for the same function, gave you different values, which means limit doesn't exist. Now, to illustrate a few examples here, let's talk about here. This is a good example. So limit x plus y everything squared divided by x squared plus y squared as xy goes to 0, 0. You can't cancel anything here. If you square the top, you're going to get x squared plus 2xy plus y squared. There is a middle term, right, for square root binomial. So you can't cancel. Can't cancel. So what you do is you say, let me check the limit on if I approach on the path y equals x. So what you have done is you just killed the whole dimension. All right? You made a two-dimensional approach one-dimensional because you established a line on which you are going to walk, and when you are walking on a line, you can only go back and forth. You can't go in space, left and right, like I had this sine line over there on an angle. So what you had earlier, what you can literally take any path to get to a line, your new domain now is line xy going through 0, 0, and you can approach that one now only in two ways. So technically, what this path does over here is reduces your problem to a Calc 1 problem. That's what it does. So when you have path equals y equal x, you will replace all y's with x's. So that reduces the problem into a limit x goes to 0, no more y's, right? And on the other side, you have x plus x squared divided by x squared plus another x squared because each y is now x. So what we did is we reduced the three-dimensional problem to two-dimensional problem because we specified a line on which we're going to walk. So now, this is going to be limit x goes to 0 of 2x everything squared divided by 2x squared, which is further equal to the limit x goes to 0 of 4x squared divided by 2x squared, and the limit appears to be 2 as you are walking on the path y equals x. So we calculated that limit is 2 on the path y equals x. Then you say, let me check another path. Because if the different path gives me different values, then we have the issue of this vertical drop, and there is no limit. So you say, okay, here in purple, let's check the path of y equals, let's say 2x, at an angle. So now your problem, your approach, looks like this. You still approach from one side, you approach from the other side, right? But it's more of an angle, right? There was a 45-degree angle here, and this is 2x. Okay, so now every one of your y's needs to be replaced by 2x. So this becomes limit x goes to 0 of x plus 2x, everything squared, divided by x squared plus, and then 2x in parentheses squared. This is further equal to the limit x goes to 0. The top becomes 3x squared is 9x. The bottom becomes 4 plus 1, 5x squared, sorry, 5x squared. And this is in the limit 9/5, which is not 2. So we got two paths. Two paths gave us different values of the limit. Remember, ant walking on a desk gets a 3, ant walking on the floor gets a 0. You cannot have 0 and 3 to be the z value at the same point, because the paperclip is either on the floor or on the desk. It cannot be in the both locations at the same time, right? It's not a cat. Schrodinger's cat, which is dead and alive until you look, right? It's a paperclip.